Hi everyone. In this video, we're going to continue on talking about conditional probability in maybe a bit more of a formal sense. So, the formal definition of conditional probability is this. For any two events A and B, where the probability B has to be non-zero, the conditional probability of A given B is equal to this. Okay, so there we have the formula. The probability of A given B is equal to the probability of the intersection divided by the probability of the conditioning event. Okay, so the conditional probability is the probability of the intersection divided by the probability of the conditioning event. So it's important to remember this definition. And now maybe this can give you an idea if you go back to our contingency table example. It might make more sense why we just picked that row for blonde when we were talking about blue eyes, given that you have blonde hair. That probability of the conditioning event down at the bottom is why we just chose that blonde row. Okay? So let's do an example, a little bit more of a challenging example, now that we have this definition of conditional probability. So the one that we had before was with just two events, A and B, and here we have three things, A, B, and C. But we're only going to consider sort of two at a time, although it may be in a little bit of a confusing way. So we have to pay close attention to make sure that everything runs smoothly here. So a news magazine publishes 3 columns entitled Art, Books, and Cinema. And so we call them A, B, and C. Reading habits of a randomly selected reader with respect to these columns are, and then they give you a number of different probabilities here to work with. That they read A is 14%, B 23%, C 37%. Then they give you the intersection of A and B, A and C, and B and C, 8, 9, and 13. And then they give you the intersection of all three. The people who get all three of them, 5%. Right? And they give you a nice Venn diagram at the bottom there to help us solve the probabilities that we're going to try to look at. Okay, so I have four probabilities here, and we'll try to get at each of them. Now, once we go through this slide, and if you're totally lost, this example comes straight from the book. And so if you are utterly confused, you can go on page 77 of our book, and they go through the example there. Okay, it won't be in as much detail as we do here, but it might be easier to read than to watch me work. So, the first probability that we're going to look at is the probability that they read art given that they read books. Okay, and so I have to do work on sort of all sides of this slide. Okay, and I'm sorry for that. It's going to look a bit scattered, but we only have so much space. Right? So number one, I'll start right here. The probability that they read art given that they read books. So that's the probability of A given B. Right? Art given that they read books. Okay? So by the definition of conditional probability, we can rewrite that as the probability of the intersection, A and B, divided by the probability of the conditioning variable, B. Okay? And so this is easy because they've given us both quantities up above. A and B here is 8%, and then B is 23%. So the probability of A given B is 0.08 divided by 0.23. Okay, 0.08 divided by 0.23. So whatever that is, that's going to be the probability. Okay, so I'm going to erase this. If I erase too quickly, just make sure to back up the video, write it all down, and then move forward. Okay? All right, so number 2. Number 2 asks, what's the probability that they read art given they read one of the other two? All right, art given that they read one of the other two. Now, this is probably the most, when you get to these type of questions, the hardest part is going to be translating from words to mathematical symbols. All right, and so we know it's the probability of A given what else? They read one of the other two. And so how I would interpret that and how the book interprets that is A given that they read B or that they read C. Okay? It doesn't say exactly one of the other two. It just says one of the other two. And so unless it says exactly, I'm not going to say one or the other, but not both. Okay? So it's A given B or C. And so we want to write that, again, using our definition that we just learned. So it's the probability of the intersection, but it's going to be the intersection of A and, we'll put in parentheses, B or C. Okay, actually, I should move this because it's going to get in our Venn diagram, which we'll need. So it's A given B or C, and that equals A and B or C divided by the probability of B or C. Okay, and so now we need to start thinking critically about our Venn diagram and where our probabilities are going to come from. Okay, so first we'll start with the bottom. I think the bottom will be sort of easier to think about. So B or C, and we can think, actually, if you want to, go back to a first definition, the probability of B or C, we can rewrite as a sum of sum and or difference of the intersection and just events by itself. So the probability of B or C we can rewrite as the probability that B happens plus the probability that C happens minus the probability of the intersection. Okay, so hopefully that's clear enough there that you can see it. So B is 0.37, B is 0.23, the probability that B happens, 0.23, plus the probability that C happens, 0.37. That gets you to 60 there, minus the probability of the intersection of B and C, which is 0.13. And so 0.23 plus 0.37, that is 0.6. 0.6 minus 0.13 is 0.47. Okay, 0.47. So we know that the bottom is 0.47. Now the top. Okay, so we have the intersection of A and B or C. Okay, so maybe it would be helpful to shade in. So I'll lightly shade in here what we're looking at. So when we look at B or C, it means we can be in either B, right, or C. And then we have to make sure to not count the intersection of B and C twice, but that doesn't really matter here. Okay, so it's those two. And so I'm looking at the intersection of A and the green stuff. And so what's that intersection? That intersection is, if I do it in purple, it's this part. So that little part, and that little part. And so what are the numbers in there? Get rid of those. 0.3, 0.03, 0.05, and 0.04. Okay, and so the probability of the intersection of A and B or C here is 0.03 plus 0.05 plus 0.04. Okay, as in this, and that. So when you add 0.05, 0.04, and 0.03, you get 0.12. And so the answer down here is 0.12 divided by 0.47. And it turns out to be 0.225. Okay. The first one was 0.348. So if we keep track, which we won't be able to up here, it's 0.348, and then 2 is 0.225. Okay, so let's get rid of all this work here. So I have to backtrack. Can't erase, unfortunately. Okay, so that was 2. Now number 3. As we hurry along, the probability that they read art, given that they read at least one of any of the magazines. Okay, so the probability that they read A, given the probability that they read just that they read A, given that they read any, so at least one of any of the magazines. So that means that they could read A, or they could read B, or they could read C. Okay? They read A or B or C, or they may read 2, or they may read 3. So A or B or C encapsulates at least one. All right, and so again, we would rewrite this as the probability of the intersection of A and A or B or C divided by the probability of A or B or C. Okay, so A or B or C. And so that is, if you look at the Venn diagram, it's going to be any of them. It's going to be in here, right? Or B or C. And so we had, the book shows a general formula for doing A or B or C. Okay, and I'll write it over here. The probability of A or B or C is that you add the singular ones, then you subtract away. You've double counted the intersection of the 2's, so minus the probability of A and B, minus the probability of A and C, minus the probability of B and C. Okay, and then when you've done that, you've then taken away too many of the intersection of all 3, and so you have to add in the probability of A and B and C. Okay? So that's the formula. It's a large formula, and I won't show all the work here. I'll get rid of this. Okay. It turns out that A or B or C, and we'll get rid of the green lines too. When you add all that stuff up together, it is 0.49. Okay, and so you could take the hard way actually and do 0.49, or the Venn diagram gives you, the people who don't read at all, which is 0.51, and so A or B or C is going to be 1 minus none, right? 1 minus, if we think about, the probability of A, where we say A is at least 1, is equal to 1 minus the probability of the complement of A, which is whatever is not A, and the complement of at least 1 is none. And so we could use this, which is much easier than what we did before. Okay, and so 1 minus 0.51 is 0.49. But anyway, the bottom is 0.49. Okay, the top, I want the intersection of A and A or B or C. Okay, and so the intersection of A and A or B or C is just A. Okay, that's the only thing that's in the intersection of A and A or B or C. So that's adding up everything in A, okay, or really it's just the probability of A happening, which is 0.14. 0.14. And so then you divide 0.14 by 0.49, and the answer there is 0.286. 0.286. Okay, so then once we get rid of this, we can do number 4. Point 4. What's the probability that they read art or books given that they read cinema? Okay, so that is A or B, right? Art or books, given that they already read cinema. So again, by the definition of conditional probability, we have the probability of A or B now intersect C divided by the probability of C. So that's easy. That's 0.37. We get that from above here. And then the intersection of C and A or B, right? That is going to be 0.4, 0.5, and 0.8. Sorry, 0.04, 0.05, and 0.08. Okay, the intersection of C and A or B are those three little intersection spots. And so then 0.4 plus 0.5, 0.04 plus 0.05 is 0.09, plus 0.09, 0.09 plus 0.08 is 0.17. So then that's 0.17 divided by 0.37, and the final answer there is 0.459. Okay, so I know that was a lot, and that took us a little while, but hopefully that gives you an idea of sort of what I expect what we're going to do with these conditional probability problems. Okay, so we'll go on for just a little bit more here. The definition of conditional probability leads us to more important rules, and so the more important rule here is what's called the general multiplication rule. And it says this: the probability of the intersection is equal to the conditional probability of B given A times the probability of B. So times the probability of the not conditioned part. Okay? And because of the intersection, it can also be flipped around that A given B times A is also the probability of the intersection. Okay? And so these rules here are used a lot in different circumstances. All right? And so that's where we're going to stop for this video. In the next video, we're going to pick up with something very important called Bayes' theorem.